Hello and welcome to this IChemE Global Awards webinar. The IChemE Global Awards celebrate chemical, process and biochemical engineering excellence and are widely recognised as the world's most prestigious chemical engineering awards. Today we'll be announcing the winners of the IChemE 2020 Food and Drink Award and the IChemE 2020 Water Award. Both winners also qualify as finalists for our top prize, the Outstanding Achievement in Chemical and Process Engineering Award. So let's get started with the IChemE 2020 Food and Drink Award, sponsored by our Food and Drink Special Interest Group. This category recognises the best project, process or product to demonstrate chemical engineering excellence in the food and drink sector. And we have two finalists. They are a joint entry from Biocatalysts and UCL and Oxford Nanosystems. I'm pleased to say that both finalists are with us today to give short presentations on their work. Subject to time, we'll be inviting you to participate in Q&A at the end of each presentation. You can ask your questions via the questions box in the GoToWebinar portal. So first up, please welcome from Biocatalysts, Davy Rowan and Andrea Rayat.
Hello everyone, can you hear me? Can you see me? I hope that's a yes. And can you see my screen? Okay. Hello everyone.
Yes, your screen, Davey.
We can? Okay, great. My name is Davy Rowan. I have an MEng in chemical engineering from the University of Edinburgh and made a transition to biochemical engineering via an MSc in industrial biotechnology at the University of Strathclyde. As of last month, I'm a process improvement scientist at Biocatalysts Limited. And today I'm here to talk to you about the project I worked on as a knowledge partnership associate for the past 2 years. This was a collaboration between Biocatalysts, who are based in Wales, and University College London Biochemical Engineering Department. The project was Ultra Scale Down Accelerates Industrial Enzyme Manufacture. To give you a little bit of context on Biocatalysts, we are a global specialty enzyme company and part of the Brain Group. We offer off-the-shelf enzymes for food and related industries, as well as providing an award-winning service package that provides customized enzyme discovery, development, and manufacturing. We partner with companies across a broad spectrum of markets, taking novel enzyme ideas from concept through to routine manufacture in under 18 months, which helps them gain competitive advantage with their new product development. And before the KTP project began, oh, sorry, I skipped ahead there. Let's try again. Before the KTP project began, Biocatalysts had already embarked on a £6 million investment in enzyme manufacturing, an ambitious expansion which is now being commissioned. Just to give you an idea of the scale, the upper walkway there is about 4.5 meters high. From the beginning, Biocatalysts were determined that advanced biochemical engineering expertise was critical to their future success. And to develop this expertise, University College London was an ideal partner based on its cutting-edge research in bioprocessing. Hence, this KTP was proposed. So UCL's innovative ultra scale down equipment and methodology in particular was identified as important to integrate. The purpose of ultra scale down is to enhance understanding and to give improved prediction of process scale with small amounts of material. This means more economical R&D, fewer failures, and greater speed to production, which is crucial in our industry to retain a competitive edge. An example of ultra scale down methodology in device form is the compass shear device you can see here. It has the ability to mimic forces that bioprocess materials like enzymes and culture broth are exposed to in large-scale operations using only milliliters of material. The red region in the diagram, you can see there is a region of high shear. I'll start again. I've skipped, so apologies here. Let's try here. We combined ultra-scaled down devices to create our ultra-scaled down platform, you can see here, to mimic these downstream processing steps. In the next few slides, I'll take you through how we worked on flocculation, then centrifugation, and onwards. I'd like to highlight one particular project in which we piloted this platform. With a partner, we were looking for an advantage in the food industry. We'd identified a potentially valuable chemical in a side stream, which is a dietary supplement in fish oil. Using our MetExtra technology, which is our metagenomics platform, we were able to identify an enzyme that degrades the chemical responsible for the fishy odor, which allowed our partner to make supplement that didn't smell like fish. You can see my supervisor here, Andrea Rea, loading the shear device with material, and the centrifuge used to clarify the subsequent supernatant. At Biocatalysts, we have a 3-litre continuous centrifuge, and we just installed the one you can see behind me here, which is 22 times larger. The centrifuge bowl weighs about a ton and rotates at 4,500 RPM and thousands of litres per hour. The trouble is the feed has to be accelerated in fractions of a second to very high speeds. The process stress the material undergoes is enormous, and every week we are faced with a new biological material to separate in the machine. I can use the compass shear device with about 20 ml of culture broth to predict if this new material will be harmed, and if so, how to protect it. The KTP began around ultra-scaled down methodology, but as these things often do, it developed to become much more. During the course of the project, Biocatalyst reps, including one of our principal scientists, you can see here, ended up lecturing at UCL. While UCL academics provided their expert insight into processing issues across scales. They also organized rapid prototyping through 3D printing. You can see the CAD drawing of the scaled down impeller here as an example. And this is our ultra scaled down flock vessel, which is about 2,000 times smaller than the tank you can see there, but it's geometrically similar. Primary recovery is often the most challenging step for the recovery of intracellular enzymes, and was in this instance. However, the industrial and academic network available to me through the Knowledge Transfer Partnership helped us to rapidly explore these flocculation conditions. And combining these selective flocculation conditions with the compass shear device and scale-up principles, we were able to create these operating windows you can see here. So you can see the lab enzyme yield starts quite high with a nice area with high yield. And then as we scale up, there's shear introduced, and there's a large-scale centrifuge that means the yield becomes lower because we have high solids, but we can mitigate that by introducing a higher dilution, which is the chart you can see at the top right, and we have a nice high yield again. And then the lower charts, you can see the lab centrate solids, so they're relatively low. 100 is a nice number for us, so we'd want to operate in that region. And you can see when we introduce more shear, there's a smaller region for us to operate in. And you can see the dilution, which doesn't change things too much, which is nice. It shows our flock is robust. And in this instance, the solids are easily cleaned up through downstream filtration. You can see on the left of the charts where we began with about 40 to 50% recovery for each product, and how we were able to improve this through selecting the best conditions from our ultra scaled down predictions. We improved it to about 80%. This allowed us to greatly enhance the recovery of the enzyme I mentioned earlier and another product in development. Note that here I'm showing protein recovery, and approximately 20% of that is not our enzyme of interest. It's host cell protein, etc. So after establishing this technology, an order for this enzyme came through, and a customer needed about 30 kilos. So instead of one 500 litre producing 3 kilograms, one 500 litre fermentation was able to produce 5 in the same overall processing time. And that meant instead of 10 processes taking 80 days to complete, we're able to fulfill the order in 6 processes in 48 days. This allowed us to ship the material early, and it gave us 32 days to pursue other production opportunities. Bringing in these new engineering skills has also helped enhance product discovery by speeding the transition from test tube to a high-performing production process. We've been able to use the increased capacity to further develop many products, including one of our own strategic products, which is methionine gamma lyase. It helps to make sulfurous notes in cheese, which apparently makes the cheese more appealing. Initial scale-up work shows a good response with these high recovery techniques for this enzyme. As a collaboration, we are currently preparing a publication on some of this material, which we hope to be able to share with you all shortly to celebrate the success of this project. And here at Biocatalysts, we're always seeking to continue to marry our expert cell biology skills with improved process design to create new product opportunities of high value to our customers. The Knowledge Transfer Partnership Scheme is run by Innovate UK and supported by the Welsh Government, both of whom I'd like to take the opportunity to thank. I'd also like to thank all parties again for their contribution, particularly my UCL supervisors, Mike Hoare and Andrea Rea, and my manager, Maeve O'Neill from Biocatalysts. Thanks to IChemE for the opportunity, and thank you all for listening. Myself and Andrea will now happily take any questions you have.
Okay, thank you, Davey. So we do have a few minutes for questions. So if you do have any questions for Davey, please type them into the questions box on GoToWebinar. You should see it there on the panel. It simply says questions at the top. While I give you a moment on that, if you have joined us late and you're expecting the IChemE Water Award presentations, they will follow shortly. And also, this is one of a series of IChemE Global Award webinars taking place throughout November. This is the first of our webinars. If you'd like to find out more about what's still to come, please visit our website. That's icheme.org/global awards. That's icheme.org/global awards. So we don't appear to have received any questions, so that's fine, but thank you, Davey. We'll move on. We'll now move on to our second finalist, and from Oxford Nanosystems, it's Alexander Reep.
Oh, there we go. Right, hopefully you can see that. Good afternoon, everyone. Oh. And me as well. Fantastic. Right, well, yes, I'm Alexander Reep, CTO of Oxford Nanosystems. A quick introduction to who we are. We're a company based down in Abingdon, just south of Oxford, and consists of a team of about 15 scientists, engineers, looking to improve heat transfer in a number of different industries. We've recently raised investment and have got a nice large R&D facility with a fully equipped wet lab and some environmentally controlled thermal labs, and also an R&D development plant for coating certain different components, which I'll be talking about in a bit. So I think the first question to go through is why? What do we do and why are we here? I guess the problem that we're trying to solve is heat transfer. Heat transfer is a major issue for almost all industrial processes. Things like air conditioning, refrigeration, electronics cooling, energy generation, all of this is based on heat transfer. And the efficiency of all of these systems are based on the heat exchangers, a number of which different types you can see on the right-hand side. And this has been a very limiting factor for a number of years. And the main issue that we have with all of these different systems is it's a massive drain on our resources, as well as being a real problem for climate change. As you can see, for example, refrigeration and air conditioning alone consume 17% of all worldwide electricity. Commercial refrigeration, which is also the main focus at the moment, is 3% of all electricity in the UK. And all of these systems emit almost 7% of the total greenhouse gases. But with global warming increasing, this is looking to increase as more and more people are going to be needing air-conditioned systems, as you can see by 2030. And so this is a massive issue, and really it's a sort of a circular issue that as more of it's used, then the world's going to heat up more. And so what are we looking to do? Well, we've developed NanoFlux. NanoFlux is a coating technology that we can coat on the internal surface of a multitude of different types of heat exchangers. And what it does is significantly improve heat transfer in any sort of two-phase system. So anywhere where you need a liquid to boil, which is all refrigeration, all air conditioning, we're able to show that you can increase heat transfer by over 500%. This is all being tested by Brunel University. So these are massive improvements in heat transfer. Nice thing about our system is that it's a low temperature, so it can be used at sort of below boiling point of water. And because we can coat sort of the internal structure, we can coat all of these kind of heat exchangers after they've been manufactured. So there's a large retrofit possibility here. To give you some examples of what we mean is we've given a few different types of heat exchangers here. Top left here is a brazed heat exchanger. Most people will have one of these in your sort of domestic boiler, but these have sort of been very used in heat pipes, air conditioning systems. They're sort of all over the place, and they're sort of in some ways the the best way of transferring heat at very high efficiencies. We can coat, as you can sort of see, these things fully manufactured. It's a sort of a section of one on the internal side. And we're able to put down two different coatings here to improve, although we only improve the two-phase, we just sort of show that we can coat this sort of really intricate geometry by just pumping our solution through. We've coated millimetric size tubes. These are about 1.4 millimeters ID for a project we were doing with CERN to improve the detectors at the Large Hadron Collider. And then for electronics cooling, we've also coated some sort of very small skid cold plates for use in your sort of data center cooling to sort of consumer electronics. But the one we're here to talk about for commercial refrigeration is these sort of thin tube coils. You have a refrigerant running through the internal side of this, which evaporates, and they go from anything from sort of smooth internal surfaces to sort of rifled tubing, and you can sort of see the improvements in surface area and nucleation sites that our coating has by going on the internal surface here. Very briefly, I'll go through the general refrigeration cycle. So we have an evaporator, which is sort of the main area that we're focusing on, where a refrigerant passes through and evaporates. It then comes up and goes into the compressor, where it's changed into a sort of a very hot liquid at very high pressure. This goes down into a condenser, which then goes from a gas into a liquid that stays at very high pressure. Finally, through an expansion valve, which changes it to low pressure and sort of a cold liquid, then back into the evaporator. So what we've been able to do, is to coat and test at our facilities here what our coating does on these systems. So we've got an insulated cold room setup here, where we've got the condenser and the compressor in sort of an external unit here. Our evaporators, we've got multiple units that we can test. You can sort of see one on the inside here. We've got heaters to keep the room temperature down, and we've got our electronic expansion valves at the top to make sure that we can sort of see how these things operate fully. What we're able to see when we coated one of these sort of units for a cold room was that we can, for the first coating we did, we were able to bring down the average room temperature by about 1 degree, which allows us, if we actually keep the room temperature at a certain temperature, for example, we've taken 5 degrees here, it means we can increase the temperature that the refrigerant evaporates at. So on a normal uncoated system, the evaporator runs evaporating the refrigerant at -15. The coating allows us to raise that to -10 degrees. This in turn reduces the amount of energy that the compressor needs to operate. So we've gone down from 250 watts to actually 214, which overall means that just putting the coating on the internal side of one of the heat exchangers, we can improve the energy efficiency of sort of any kind of commercial refrigeration system by 14%. This is without changing anything else in the system. So this is a very sort of significant This has a very significant effect on the system, and we're about to actually start proof of concept with some of the UK's retailers to see what this means when you actually put it into a full a system, and from there sort of go forward and look into scaling the technology up. Since that first test, we've actually been able to show that modifying the structure to actually optimize the coating for the sort of the given refrigerants, this case 134A, allows us to even further reduce the room temperature. And so the next test we're also looking to do internally is actually see what that does to the overall energy efficiency, where we're hoping that we can actually improve that 15% much, much further. So this takes us to the value proposition of what we're looking to do. So we have three areas we can work in: either sort of an increased capacity and energy efficiency, which as we've sort of seen show that these systems that we coat allow us to reduce the energy consumption by about 15%. We can make the units smaller, which for certain areas, for example, on your sort of the kind of air conditioner you've got, you can see mine up here, but sitting on the side of my wall here, we can seriously reduce the size of that, making them much better, and also reduce the refrigerant charge, but also retrofit into existing systems. So for certain areas in sort of refrigeration, if we can coat these systems after they're already in use, we can significantly improve the energy efficiency straight away. There we are. Thank you very much.
Okay, thank you, Alexander. So once again, we can take questions if we have any. Please type them into the questions box on GoToWebinar. We'll have a moment for that. If what you've been watching has left you suitably inspired to submit your own entry to next year's IChemE Global Awards, do keep an eye on our website for entry information. We typically open every year at the start of March. So March 2021, we'll be looking for entries for next year. We don't appear to have any questions, so thank you, Alexander.
Thank you very much.
Thank you. Which brings us to the moment you've been waiting for, where we reveal the winner of the IChemE 2020 Food and Drink Award. So, ladies and gentlemen, the winner of the IChemE 2020 Food and Drink Award, sponsored by the IChemE Food and Drink Special Interest Group, is the joint entry from Biocatalysts and UCL. So congratulations to you, and well done also to Oxford Nanosystems, highly commended in the category. Two really strong finalists this year for our judges to choose from. Davey, if we can get you back on the line, how does it feel to be an IChemE Award winner, our first winner of 2020?
It feels brilliant. Thanks very much. I'd just like to thank everyone again, and thank you guys for the opportunity. It's unbelievable. Thank you.
Good. Well, look, congratulations once again then to Biocatalysts and UCL, winners of the IChemE Food and Drink Award. So we now move on to our second award of the afternoon, and it's the IChemE Water Award, sponsored by the IChemE Water Special Interest Group. This award recognises the best project, process or product to demonstrate chemical engineering excellence in the water sector. Here are our finalists. We have AquaB, a joint entry from Monash University and Oxfam, a joint entry from the National University of Singapore and the Chinese Academy of Sciences Research Centre for Eco-Environmental Sciences. We have two entries from Saudi Aramco. We have a joint entry from Saudi Aramco and King Fahd University of Petroleum and Minerals, Trailblazer Technologies, and Worley Group. Once again, all of our finalists have been invited to join us today to tell us a little bit more about their work. Unfortunately, Trailblazer Technologies have been unable to join us, but we do have representation from all of our other finalists. And up first, representing AquaB, I'd like to welcome Niall English.
Thank you very much. So I'd like to talk for a while about the large advance that we've made in Dublin in nanobubbles and the applications that we have in the environmental sector, and particularly for wastewater treatment. So I'll speak on behalf today for myself, Niall English, and also my colleague, Mohammed Retzagani. So what I'm going to speak a little bit is about the background of nanobubbles. I'll speak a little bit about our innovation, our discovery of how we can make them much more efficiently in an energy sense without additives. I'll also talk about the green economy, green world implications, and then focus in a bit more detail on wastewater treatment and the details of our nanobubble generator. Then I'll finish by saying a little bit about some quite exciting recent results we've had on ozone nanobubbles and implications that could have for wastewater treatment where there's, say, a high level of bacterial contamination. So recently, in the past 10, 20 years, the interest in nanobubbles has really increased substantially, originally in the scientific literature as a sort of thermodynamic curiosity as to why do they exist. There was no real thermodynamic rationale for their existence, but exist they do, sometimes for many weeks or even months. And they're, you know, a thermodynamic conundrum because thermodynamically they're not stable, they're metastable. And the number of studies on nanobubbles has increased greatly in terms of the literature in the past 10, 20 years, with many studies motivated by bio and medicine, also agriculture, the food industry, fish farming, purification, etc. Not many studies have focused on methods to generate them, mostly on applications of nanobubbles. But we're going to talk a little bit about the methods that we've made for generating them. So in terms of further background, these nanobubbles are very tiny bubbles on the nanoscale. They're quite different from ordinary bubbles in that they not really subject so much to buoyancy forces, so they don't tend to lift and therefore rise and coalesce together, agglomerate, and then ultimately burst as micron or larger bubbles would do. So they tend to more or less stay put in the solvent, in this case in water. But the nanobubbles that we can generate are typically even more stable than nanobubbles generated by energy-intensive, say, acoustic cavitation methods and by large pressure drop methods. We've found that our nanobubbles could indeed be stable for periods of up to a year and longer. We stopped measuring after about a year and a half. And we can really increase massively the population of nanobubbles up to 10 to the 12 to 10 to the 14 nanobubbles per milliliter and beyond, indeed. And this really increases massively the amount of surface area per unit volume that's available. So this is very interesting for a whole host of applications. And we're going to focus on water treatment in today's brief discussion. To talk briefly about some other applications, not that I want to focus on them in any depth, this could also be used for carbon capture and storage, environmental remediation. For example, you could look at algal blooms in managing large water bodies, okay, lakes and so forth, but also could be used for remediation of soil, in production of biofuels, in biogas production, also in upgrading biogas. And of course, when I speak about ozone bubbles later, I'll talk a little bit about disinfection applications. But in anaerobic digestion, more specifically, I mentioned biogas a minute ago. It could be used in methane upgrade and also in having more efficient biogas anaerobic digestion production itself. One final application that we have used for very heavily polluted water is to form gas hydrates. So gas hydrates are a type of inclusion compound. It's like ice, but not ice as we know it. If you burn it atop a Bunsen burner, it will burn calorifically because of all of the methane or CO2 molecules trapped inside. But these will just float to the top if you have heavily polluted wastewater, just simply by flotation and Archimedes' principle. But if you have nanobubbles there in the wastewater, you can really boost the level of hydrates, and heterogeneous nucleation becomes all the more efficient using nanobubbles. So that can be done for wastewater treatment or desalination, or for water from fracking or heavily polluted water, even radioactive water. And this also has implications in gas storage, for example, hydrogen storage and CO2 storage as well. Now, to focus a bit more on the task at hand in today's brief talk, which is focused on wastewater treatment per se, how can we enhance the aeration using nanobubbles to have more efficient traditional activated sludge? And that's really the heart of the matter of what I'll speak about in the next couple of slides. So, you know, in terms of aeration methods, there's a variety of methods I'm sure that this panel is well aware of in the water treatment world. I mean, there's mechanical aeration, bubble-based aeration using fine bubbles, and then of course the nanobubble approach. And with our method of generating nanobubbles that we have patented and published recently in Science Advances, we have 3 PCT filings as well on the way. We can reduce very substantially the energy cost of nanobubble generation. So because we're using DC, direct current electric fields, to generate nanobubbles by effectively sucking the water in by an electrostriction method, the energy cost for that is practically, well, not quite zero, but it's about 30 to 40% efficient if you look at the minimum thermodynamic bubble nucleation energy versus other pressure drop based methods, which would be, you know, 1,000th of 1% efficient compared to the thermodynamic limit. So we can really target that 2/3 of energy costs of wastewater treatment, which of course is aeration. And if we can slash that down to very, very substantially, almost down to naught, you're effectively saving 0.5 to 1% of a developed country's electricity supply every year. And we have trialed this in our laboratory, doing activated sludge experiments in our laboratory itself. Some of the cost implications that I've spoken about in terms of capital running cost, I've shown here on the left in terms of a cost breakdown rolled up into the net present value between fixed and variable costs. And you can see that it's substantially lower for our nanobubble based aeration in red, where we're effectively eliminating the aeration electric demand and not having to have pumps and the capital costs associated with the pumps in our settling tanks. But if we look here on the right, I'm showing you 3 vials. On the leftmost is a treatment, traditional treatment, where there wasn't any treatment applied at all. Sorry, no treatment. Then in the middle we have traditional activated sludge and using fine bubble aeration, which is sort of state of the art at the moment in the industry. And then we have used nanobubbles to really have a much better level in only 3 hours. And our generator is essentially here. I've shown various generations of our generator, but this is essentially based on applying electric fields without any direct contact with the electrical wire, so there's no electrolysis. And you can get favorable surface area to volume ratios. Finally, for ozone nanobubbles, we have managed to make ozone nanobubbles, and we can deploy these in both the liquid form with half-life 5 times longer than traditional ozone bubbles, and we can also deploy these in a spray mode to target various types of viruses, for example, SARS-CoV-2 and other viruses. And we're currently doing testing on effectiveness at killing SARS-CoV-2 and, of course, other prevalent viruses. So we can take heavily polluted water that's biologically polluted with lots of viruses and really increase the half-life of ozone in water in nanobubble form that really serves to kill bacteria much more effectively. So thanks very much for your attention. My email address is there along with my colleague Mohammed Ratzagani. If you do have any follow-up questions that we can't answer today, feel free to send us an email. And thank you very much for your attention.
Okay, thank you, Niall. Once again, then, if you have any questions for any of our finalists, please use the questions box on GoToWebinar. We do have a question, several questions. So the first one here, just to clarify, is it correct that you project the water to a DC to do the electrolysis?
Electrolysis is a misnomer. There is a DC electric field, but the wires and the electrodes are covered by plastic or a type of hydrophobic coating so there's no direct electrical communication or contact between the underlying conducting metal and the water.
Okay, thank you.
But it is a DC electric field, yes, but electrolysis, no.
Okay, thank you. Why do you call them nanobubbles, and why are they stable for a long time?
Well, you're getting into one of those classic conundrums. We call them nanobubbles simply because they're nanoscale in size. The typical diameters would be 50 to perhaps 250 or 300 nanometers, and they're smaller than microbubbles. In terms of why they're stable for a long time, that's the source of vigorous debate. I mean, technically they're thermodynamically metastable, but they're kinetically stable, often for weeks to months. We think it's because of a delicate balancing act of forces between a surrounding dielectrophoretic layer, where you get partial alignment of the water molecules' dipoles, and you also have apparently a mass buildup on the gas side of the bubbles as well, and this serves to stabilize them once you do detailed molecular force balances. So that's our current best estimate as to why they're stabilized. I emphasize metastable, but for many weeks and months.
Okay, thank you. That rounds off the questions. So thank you, Niall. It's time to move on to our next finalist. And this is a pre-recorded video from Monash University's Jiwang Zhang.
Good afternoon. My name is Jiwang Zhang. I'm a professor at Monash University in Australia. Due to the time zone difference, it is a challenge for our team to attend this online webinar. So we decided to pre-record this short video, giving you a brief introduction to our project. This project is a collaboration between Monash University and Oxfam Australia. Oxfam works to strengthen the community's recovery capacity against the impact of the drought, outbreaks of the waterborne diseases, and the risk of the conflict due to the limited access to safe water. While Monash is a home to one of the largest research hubs in the country in the area of the energy-efficient separation, with the decades of the expert on the use of the latest membrane technology that are highly efficient and require low maintenance. Over the last 3 years, Monash University and Oxfam Australia have been working closely, aiming to develop a low-cost solar-driven desalination technology for resilient clean water supply in the rural community who are impacted the most. Ensuring universal access to the safe and affordable drinking water for all is one of the United Nations Sustainable Development Goals. A universal call to action and end poverty and ensure that all people enjoy peace and health. Addressing this challenge is crucial. Monash University and Oxfam Australia both are committed to improve the people's quality of life by innovation. While large cities like Melbourne have access to large water infrastructure, a centralized water supply system where electricity and chemical are required, but remote communities do not have those access. Power is costly and limited, especially for communities that live off-grid. Salinity in many water sources is on the increase due to the climate change, drought condition, Additional contamination issues arise from the naturally occurring chemical like the fluoride arsenic. All those contaminants and salinity pose health issues. Although the salinity is only a few thousand ppm, the health consequences of drinking those saline water and contaminated water are serious. Consequently, cause reduced productivity and lower income due to the illness. To address this issue, this project aims to develop decentralized, low-cost desalination technology, which will be driven by renewable solar energy. And this technology is targeted rural and off-grid area, which has limited access to chemical, to electricity. And this technology can improve the access to the clean water for the better health. We started this project in 2018 in our design to reduce energy consumption. Low pressure reverse osmosis membrane were used, which is able to remove bacteria, soluble ions, and other contaminants, producing high-quality clean water. By appropriate pretreatment design, we minimize the maintenance requirement. The system is fully powered by a foldable solar panel, ensure it can be run off-grid. All components are assembled into a suitcase, making it very compact, can be shipped to anywhere where it is needed. Over the last 3 years, we gradually improved our design from the first generation to the third generation, which is now ready for mass manufacturing. Currently, we are working with regional community to implement this technology to provide clean water for the remote communities. I would like to take this opportunity to thank the fantastic project team from Monash University and Oxfam Australia, Eleanor, Saba, Jamie, Katie, Paul, Meipeng, Yue, Yun, Lena, and Fazana. Thanks them for their great job. I also would like to take this opportunity to thank Monash Infrastructure City Grant, Perpetual Impact Grant, Lord Mayor Charitable Foundation for their financial support. Last but not the least, we would like to thank IChemE for giving us this opportunity to share our project. If you have any question or want more information, please feel free to send me an email. Thank you for your attention.
Okay then, so Zhiwang's unable to be with us today, so I'm afraid there's no live Q&A, but as he says, do get in touch if you want to know more about that one. Our next speaker was due to be Jae-Paul Chen from the National University of Singapore, but unfortunately he's also unable to be with us this afternoon, so instead we'll move on to our next finalist, and it's the first of our entries from Saudi Aramco. So please welcome Amir Abdel Fattah.
Hello. Can you see my slides? Can you hear me?
Yes, we can.
Yes, we can, Emil.
Thank you. Yeah, I wasn't prepared. I think I was the one after one. So, well, thank you all very much. It's a pleasure to be here, and it's an honor to share with you our technology on acoustic oil water fine separation. This technology was developed mainly for downhole applications, but can also be used for surface applications to separate oil and fines from water. My name is Amr Abdul Fattah. I'm from Saudi Aramco XPIC Advanced Research Center. So what is the problem we are trying to solve here? The main problem is the increasing volumes of produced water worldwide. So as you all may know, as more oil reservoirs get depleted, more oil comes with the more water comes with the oil, and the ratio of water to oil increases as the reservoirs get more and more mature. These volumes of produced water present serious environmental and health hazards. Health hazards to those who are handling the process of getting this water, removing the oil from the water to use the oil, processing the water, treat it, and dispose it back into the reservoir. And the environmental hazards can be summarized as those posed to underground and shallow groundwater aquifers and surface water resources as well. As you can imagine, with these huge volumes of produced water, the process is energy intense, very costly, and poses serious sustainability issues worldwide. Current technologies developed for downhole applications for separation of oil from water downhole, like hydrodynamic methods such as hydrocyclones, gravity separators, and membrane filtration methods. These are new technologies that are being evolved, but they have some drawbacks. Mainly is the intervention with the flow of the fluids, which causes pressure drop and intervention to the fluid flow. And these technologies can hardly remove the fines, the solid fines from the water. If you think of membranes can remove the solids, then the problem would be the fast fouling or quick fouling of these membranes and the lifetime of these membranes. These methods are also not tunable, so it's not easily, these are not easily tuned to accommodate changes in flow rates and changes in the water to oil ratios coming in the production wells. If you want to do any maintenance, if you want to replace something, you have to do workover, and workover is a major operation that is very, very costly to do, besides, of course, shutting down the well and stopping the resources. Gravity, of course, as you may know, if we count on the gravity alone, it's good, but it takes a long time to separate the oil. So what is the solution we're proposing is acoustic separation. And acoustic separation is a very well-established technique, and I'm going to get into the some details of the science about acoustic separation in the next slide. But these methods are intervention-free, so they do not intervene with the flow. They do not cause any pressure drop, because basically you supply the acoustics from the peripheral of the conduit where the flow or the fluids are flowing. They can distinguish very well between solid fines and compressible oil droplets in the water, so they can distinguish between the two. They can be remotely controlled and tuned to accommodate changes in flow and water to oil ratios. And there is no preset flow is required, simply because you can tune the acoustic configurations to accommodate the flow rates. The science behind acoustic separation is simple and has been out for more than a century, and it's called acoustophoresis. It's basically the phoretic migration of objects in solutions or in fluids under the effect of sound waves. So when we excite a standing wave in a solution, we create what's known as pressure nodes and pressure antinodes. And the pressure nodes and antinodes, or the opposite would be displacement nodes and displacement antinodes, they create direct radiation forces that act directly on the suspended particles or droplets in the solution. And this equation, which is the well-known Rayleigh's equation, as you can see, acts on the particles, and it's a function of the contrast in density and compressibility between the suspended objects and the continuous fluid around them. So this combination of density and solid and compressibility and density is what determines if solids, the solids which are less compressible than the water can migrate towards the pressure nodes, while those droplets, oil droplets, that are more compressible than the water around them will migrate towards the pressure antinodes. So we can separate the solids and the oil droplets in separate locations in the conduit. So as this cartoon shows, and the most important thing here is that the forces act only on the small tiny droplets, on the suspended droplets. So the force, the power that's needed to affect and migrate and displace these droplets or fines into the pressure nodes or antinodes is very, very small, in the range of nanonewtons at the most, to move them a distance of maybe 1 centimeter or so. So the concept of our technology is based on creating acoustic standing waves across the conduit in which the fluids are flowing, the water, oil, and fines. So you can imagine a production tube in the reservoir or the production well itself. And when we apply acoustic waves and create standing waves of decreasing node or decreasing loop number, so the number of nodes or number of loops decreases in the direction of flow. So by doing it this way, we can separate the oil and harvest the oil towards the center of that conduit and push the fines towards the sides of the conduit. To prove that concept in the microscopic scale, so we ran experiments with different combinations of oil droplets and solid fine particles, different acoustic configurations, and to actually verify and confirm our observations with the theory that I just presented. And as you can see here in this microscopic scale experiments, these lines, these dense lines, these are the oil and the fines, all separated in separate locations in the pressure nodes and pressure antinodes, and these are separated by half a wavelength as the theory predicts. Having proved the concept at the microscopic scale, we move to the macroscopic scale. We applied the same principle on a conduit that's about 10 centimeter by 10 centimeter, that also contain the oil droplets, solid fines, and again, we can observe the separation as the technology or as the theory predicts. So, but after doing that, then we move to the full scale, the field scale size, as a laboratory tool where we can test it and quantify the separation under more systematically, if you would. And the one you see here on the right is the actual field scale prototype, and it's comprised of 6 stations of different acoustic stations that can create standing waves of different loop numbers in the direction of flow as I described, and can be controlled via this control box that you see here on the left. So we ran a few experiments under different conditions, 6 stations as I mentioned, ranging frequency between 90 kilohertz to 240 kilohertz. So, and we start, so the higher frequency gives the larger number of flow loops. So that would be in the beginning or at the entry of the fluid, and then it goes down all the way to the 90 kilohertz, where the oil is expected to form towards the center and the solids towards the side of the conduit. And we ran these experiments at flow rates at something above like 500 barrels per day flow rate. So as you can see here, this is a snapshot of one of these experiments that shows that the separation is happening as we predicted it, and eventually separate the oil towards the center of the conduit. What are the benefits of such a technology? For oil and gas upstream applications in general, if we use it downhole, we will save a lot of energy, because we're using the downhole pressure to flow the fluids and only acoustics to act on the suspended oil droplets and solid particles. By doing this, we can take the water downhole and re-inject it into a non-producing formation in the reservoir, so we can get rid of the water before it even comes to the surface and produce more oil towards the surface than water. By this, of course, we reduce these environmental and health hazards. Also, by doing this, by removing the solids, we can prolong the life of the electric submersible pumps. These are very, very expensive pumps that are used for artificial lift, that are used downhole to bring the fluids to the surface. And fines, of course, reduce the lifetime of these pumps. If we use the tool on the surface, so we can do the same, separate oil, water, and solids from the water. So we can get rid of the water right away before actually going to the processing plants, the GOSP. And so that will help us to avoid upgrading and modifying the GOSPs to accommodate the changes in oil and water ratios. We reduce the environmental hazards again. We can also reuse that water that we are cleaning and removing the solids and oil from, and can use it again in water flood operations. So we can reuse the water in our operations. It's low maintenance, because if there is anything, we do not have to shut down the well and do a workover. And the last thing is, it's also, when it's used on the surface, we can combine it with multi-phase flow metering, or actually replace the multi-phase flow metering by single-phase flow metering, since we can measure the flow of oil by itself and the water by itself. For other non-oil and gas applications, the tool is suitable for in situ purification of municipal and agricultural water, again by separating let's say solid contaminants or oily contaminants, and removing these by using the acoustics, so we can purify and clean the water. Or it could be a hybrid system that can assist and can be combined with other filtration techniques to prolong and make these other techniques even more efficient. We can use the tool for water recycling operations, so we clean the water and reuse it for other industrial application. We can use the tool to isolate contaminants and even detect the type of these contaminants, since we are able to isolate them in high concentration, so we can detect them. And finally, the tool can be used as a demulsifier when we have oil in water emulsions and we want to demulsify the oils to form larger oil or oily substances and so on. For sustainability, It's, as you can imagine, by using this kind of low energy tool, we can do oil production and increase the oil production efficiency, since we're getting more oil to the surface than water, as in the current operations. And we can do this at lower cost, lower carbon footprint, and less environmental hazards. We can do direct disposal of the produced water without any handling to reduce the health hazards. And we can utilize the water in other operations, as I had just described, and doing all this with low energy consumption. Thank you all for listening, and my email is in the right, the bottom right, if you have any questions or have any follow-up comments. Thanks for listening.
Okay, thank you very much. Once again, we have time for questions, so please type them into the questions box on the GoToWebinar portal. Our first question is, could acoustic wave enhance the oil recovery or reduce water cut?
Yes, that's the main purpose when it's used downhole. So by using it downhole, we reduce the water cut going to the surface. So the water that's coming with the produced fluids going to the surface would be less, since we can dispose of it downhole. So for that purpose, it's going to reduce the water cut. But in terms of how much water is coming to the surface.
Okay, thank you very much. There are no further questions, so we will move on to our next finalist. And we have another Saudi Aramco presentation up next. And this one is Faisal Al-Karouni. Over to you, Faisal.
Hello, can you see my screen?
Yes, we can, yes.
Sorry. Okay, thank you. Ever since the discovery of oil in Saudi Arabia back in 1938, Saudi Aramco has become the world's leading oil producer. But born of necessity, as an energy company in a desert nation, leading the world's production means very little to us without environmental stewardship. Therefore, we have long been pioneers in water conservation. Ladies and gentlemen, today I'm glad to share with you one of Saudi Aramco's latest initiatives to conserve the natural, scarce, and non-renewable resource, groundwater. Before we go any further, I would like to ask each one of you a question. Do you know why groundwater is used in our production in the first place? Well, this is because of the oil required specifications prior to exportation or refining. When oil is first extracted, it gets processed at the numerous gas oil separation plants or GASPs across our country. These GASPs receive wet crude oil and separate it into three main categories: water, gas, and dry oil. At these GASPs, we ensure that the dry oil meets two main specifications. The first one contains the water content in oil, which is also known as basic sediments and water. The water content has to be less than 0.2% by volume, and this is achieved by some techniques such as injecting some chemicals. The second required specification, which is the one relevant to our topic today, is the salt content in dry crude. Salt content has to be less than 10 pounds of salt per 1,000 barrels. Oftentimes, this is achieved by washing the dry crude with groundwater, a process that is known as desalting. To give you a more clear and detailed picture, let me share with you a simplified schematic of the GASP process. And again, GASP stands for gas oil separation plant. Once oil is extracted, it comes with associated gas, water, and other contaminants such as salt. At our GASPs, the wet crude is processed and separated as follows. the crude enters to the high pressure production trap, a three-phase separator where oil, gas, and water are separated by gravity. Let's focus on the oil path for now. Oil then flows to the low pressure production trap. This is a two-phase separator where oil and heavier gases are separated. Then the crude is pumped to the desalting train. It first goes to the dehydrator, where emulsified water droplets are separated by electric coalescence generated by the top-mounted transformers shown in green. At this stage, the oil is dry already, but it passes to the desalter to remove the wash water. Now, where does this wash water come from? It is groundwater that's mixed with oil before entering the desalter. This is done in order to dilute the high salinity residual water in oil. Then water is separated from the water separated from the vessels is sent to the water oil separator, where it is de-oiled before it's injected back to the reservoir. And ladies and gentlemen, here where we have identified an improvement opportunity. The idea is to use the produced water from the water oil separator instead of the groundwater to wash and dissolve the oil. But can this be done immediately? What are the challenges here? As a matter of fact, the produced water cannot be used immediately because there are some parameters that must be met first. First of all, the total dissolved solids, TDS, which must meet certain specification, is very high in the produced water, making it incapable of washing oil. Also, although the produced water is de-oiled at the oil-water separator vessel, as we have seen earlier, it still contains fractional amount of oil. This oil is not necessarily processed, and therefore it could affect the quality of our produced oil. Last but not least, the produced water is sour and contains H2S, which adds complication. These challenges differ from using the produced water to wash oil. Unfortunately, the technologies we used in the past had some limitation. However, earlier this year, we implemented the vacuum technology, which helped us to overcome these challenges. Let's have a closer look at it. The technology uses vapor compression crystallization water treatment design to treat the produced water. The vacuum technology processing unit takes the produced water and treats it. We used this treated water to wash our produced oil instead of groundwater. Now let's take a closer look at the vacuum technology. The produced water is pumped and mixed with the caustic acid at the suction of the brine circulation pump. This is done to neutralize H2S inside the process water. The pump then pumps the brine water at high flow rate through the primary heat exchanger, in which the brine is heated by the compressed vapor flowing from the rotary blower before it enters the vessel. Due to the low pressure, once the brine enters the disengagement vessel, partial flash vapor is generated and sucked by the rotary blower and the remaining water goes to the bottom of the vessel, which is then circulated by the pump. The rotary blower compresses the generated vapor and increases its temperature. The compressed vapor then exchanges heat with the circulated brine in the primary plate heat exchanger, condenses as a product, and collected in the distillate tank. In case the feed produced water is of low temperature, then the condensed vapor can be used further to preheat the feed water. A caustic neutralization tank is connected to the distillate water tank to recover any vapor water that has not been condensed and it contains H2S. To avoid high concentration, the brine to avoid high concentrations of the brine, intermittent blowdown is conducted at the pump. So by using this approach, we were able to find an effective alternative to groundwater. The challenges that have been introduced earlier were overcome as the TDS values through this vacuum technology were acceptable. In addition, the oil presence was no problem as no foaming was observed from the sight glass from the tank or the vessel. Also, the injected chemical was able to resolve H2S issues. So, by using this technology, we were able to find an effective groundwater alternative to produce high-quality hydrocarbons and save groundwater for future generation and other sectors such as agriculture. Thank you very much for your listening. This is the end of my presentation, and here's my email as well. If you have any questions, I'll be more than happy to answer them.
Okay, thank you, Faisal. Once again, it is time for Q&A. If we have any questions, please type them into the questions box. Whilst we have a moment, this is a good time to express our thanks to all of our volunteer judges. The head judge is Keith Batchelor, and he leads a team of volunteers who work tirelessly to review and score every entry we receive across all of our categories. You can find out more about the judging panel on the IChemE Global Awards web pages. We don't have any questions for you, Faisal, so we will move on. Thank you very much. Our next finalist is Saudi Aramco again, but this time it's a joint entry with King Fahd University of Petroleum and Minerals. And to tell us about this one, it's Fahd Al-Ghanhami.
Hello, can you see my screen?
We can hear you, but we can't see your screen yet.
Okay.
I think it's just coming on now. Just give us a moment.
Can you see it? Can you see it now?
No, we can't. It's a white screen. Perhaps if you unshare and then try sharing again.
Okay.
There we go. Yes, we can see you now.
Okay, good. Okay, thank you very much.
Okay.
Okay, good afternoon, ladies and gentlemen. My name is Fahd Al-Ghanhami from Saudi Aramco, and on behalf of my team, it's my pleasure today to present briefly about our newly synthesized adsorbent materials, which we call it POG75, for oil removal from water. This work is a collaboration R&D work between Saudi Aramco and King Fahd University of Petroleum and Minerals. Can you see the second screen, the second slide?
Yes, we can, yes.
Okay, good. Our motivation for this work is to develop an adsorbent material to remove oil from produced water. And as you see here in this slide, by reducing the oil content without desalination, we can use the produced water for different applications like flooding and fracturing. And the advantages of this adsorbent material, we can for sure say that we can reuse the produced water by removing the oil. Also, we can recover the oil that will be adsorbed by this material. Moreover, by this material, we can utilize it to remove an oil spill from seawater. And also, by this material, we will help the environment by reducing the wastewater, by removing the oil content, and reuse the water in any other applications. Successfully, as I mentioned, we synthesized the novel and cost-effective hydrophobic adsorbent polymeric material based on the grafted graphene. The graphene was derived from graphite and modified with 9-octadeconic acid to obtain the 9-octadeconic acid grafted graphene. The resulted material, we call it BOD75, and as you see it here inside the green box. In this slide, as you see here, this is the structure for our novel BOD75. And in the right picture, this is the spectra of FTIR, where we show here the graphene and the 9-octadeconic graphene. We perform a performance test, and we found that this material has the ability to absorb oil content from produced water in a few minutes, and as you see here in this tube. The blue liquid, as you see it in the tube here, it's the water, and the colorless liquid, it's the non-organic liquid. We use here heptane and hexane. Our mixture was based on a mixture of 0.5 milliliters of hydrocarbons and 4.5 milliliters of colored blue water. We found that the BOD75 absorbed all hydrocarbon liquid in a few minutes, which give us a high potential to use this one specifically for produced water treatment. This material shows a very fast uptake of a certain quantity that it shows the high hydrophobicity nature of this material, which repel the water as confirmed by a contact angle which goes around 150 degrees. During also the performance test, we noticed that this material, which has a higher ratio of 9-octadeconic acid, it shows that if we increase the 9-octadeconic acid, the ability to remove the oil, it goes even higher. This is why we started from percentage of 25, 50, then we reached to 75, where we reached to the optimum optimum compound that we could we will be confident to remove the oil content from water. Therefore, we believe as a team this material will has a high potential to be used in near future for produced water treatment, which give us an opportunity to help the environment by reducing the wastewater. Also, it will help us to use the produced water in several applications like flooding, or even we could go more and use this water to develop fracturing fluid and help us to save the groundwater. This material has been filed in a patent, and the patent has been published, as you see here in the right, in the right patent, and the right hand. It has been published in May 28, 2020, and also the work has been published in a high-ranked journal, Journal of Cleaner Production. And by this, I end my presentation, and it's my pleasure to answer your questions. Thank you.
Okay, thank you once again. So if we have any questions, please type them into the questions box on GoToWebinar. I mentioned earlier that we have plenty more IChemE Global Award webinars coming up this month. Tomorrow morning, we have our Young Industrialist Awards webinar, and tomorrow afternoon, we'll be announcing the winner of our Research Project Award. So if you'd like to join us for either of those, please head to the IChemE website and you can still register. We don't appear to have any questions for you on that one, so thank you very much. We'll move on. It is
Thank you, Matt.
Thank you. It's our final finalist to hear from, and it's a pre-recorded presentation from Worley Group, but we will have live Q&A with the speaker after the video.
Hello, my name is Avinash Kar. I'm a lead process engineer working with Worley Group in Louisiana, United States. Worley Group is a worldwide team of consultants, engineers, construction workers, and data scientists, all with one thing in common: we love to be challenged. Every day we come to work to solve the complexity of energy, chemicals, and resources. Today, I'll share some details about the topic, novel above ground neutralization system. So before we get into the details, let's talk about the background of ion exchange regeneration and the neutralization process. So ion exchange process produces the demineralized water. So demineralized water is required in any chemical manufacturing facility, either to produce steam or to be used inside the process operation for a manufacturing plant. If the water used in the boiler is not demineralized, it can cause scaling. It can cause scaling and eventually damage the boiler tubes. So the demineralization process uses ion exchange technology. Ion exchange technology consists of a cation and an anion resin bed. Ion exchange resin comprise of ionic functional groups like sodium ions, chloride ions, supported on organic polymeric beads. These functional groups have affinity for ions of opposite charge in the liquid stream. The feed to the ion exchange bed is often treated with equipment such as clarifier, anthracite filters, etc. to avoid plugging of ion exchange beds. Regeneration of ion exchange bed utilizes caustic and acid in several steps to regenerate the ion exchange polymer bed. The process of regeneration creates basic and acidic waste which needs further treatment before disposal. The waste stream generated is collected in a vessel or a pit and neutralized with acid or caustic addition to reach a desired pH, usually between 6 to 8 pH range, before disposal to the ditch. So let's learn a little bit about the existing the neutralization process and its drawbacks. So existing neutralization process that we are dealing with today consists of a neutralization pit. It has an impeller for turbulence and mixing. It has a pump for transfer of liquid and a pH controller, not shown in the figure, but it's there to control the pH. And presently, as you can see in the table, presently we have about 27,000 US gallons of cation bed waste and about 24,000 US gallon amount of anion bed waste coming out of single regeneration from 250 gallon per minute ion exchange train. So there are several drawbacks to such process. First is it produces higher neutralization waste volume to process. Also, it needs higher neutralization time, usually between 3 to 4 hours. It is difficult to control the pH because of various dilute streams being added. It needs excess amounts of acid and caustic due to constant fluctuation of pH, and one cannot expand the capacity of ion exchange beds due to limited neutralization capacity. And also it reduces flexibility of regenerating two ion exchange trains at the same time or simultaneously. And this is usually needed for higher demineralization water throughput. So let's learn about the novel neutralization process. So like I said before, we separated out the dilute stream and we said we can safely send that to a ditch, and the rich streams, which are also shown in the green color in these two tables, will be sent to the neutralization tank or the pit. In this case, we had a exist neutralization pit volume, so we utilized that, and we added a new tank to process new volume. So in the modified neutralization process, about 19,000 total US gallons are sent to the neutralization process, and the other stream can straight go to the ditch without processing. And one can achieve the following benefits with the new process. It lowers the neutralization waste volume about less than half of existing process. It reduces neutralization time required to just about 15 minutes, a huge improvement from 3 to 4 hours that we previously saw. pH control in this process is much easier because there are no dilute streams and less fluctuation in the pH. Also, it reduces the acid caustic intake amounts roughly by 22% from the previous process, and one can expand the capacity of ion exchange beds by adding a parallel ion exchange train because we now have a higher neutralization capacity. One can regenerate two ion exchange beds simultaneously. That will create a flexibility in the process. So these are our conclusions and some industrial benefits. The new process creates the following sustainable benefits. So about 63% reduction in the volume of ion exchange regeneration waste stream, about 62% reduction in the capital cost by eliminating and optimizing equipment design, about 55% reduction in operating cost by optimizing pump and the eductor design, about 22% reduction in chemical intake in the process, and some industrial benefits are this is the environmentally sustainable process. This reduces the number of equipment required, and also it reduces the chemical usage in the process. So debottlenecking philosophy, which is followed in this process, can be utilized anywhere to reduce waste volume for any neutralization process in the industry. And the modified process has a wider range of application in chemical, water, and oil refining in industrial operations. And this was also implemented in one of our clients' plant location with great success. With that, I conclude my presentation, and thank you for listening in. I would be glad to answer any questions you may have. Thank you again.
Right then, Avinash Kumar is with us on the line. So whilst that was a pre-recorded presentation, we are able to take questions. So once again, if you do have any, please type away in the questions box. We'll just wait a moment for that. And I'm pleased to report that Paul Chen from the National University of Singapore, who wasn't able to join us earlier, has managed to join us. So we will hear from our last finalist in just a moment. We don't appear to have any questions for Avinash Kumar, so thank you for being there. We will now move on then to our final finalist, definitely this time. It's Paul Chen from the National University of Singapore.
Can you hear me?
Yes, we can, yes.
Okay, super. Sorry that I missed the first part. All right, I'm Paul Chen from National University of Singapore, together with my PhD student, Dr. Jingyi Li. And I also have a research collaborator, Professor Ma, who is from CAS, China. In this particular research work, we have actually include 3 parts. The first part is microplastic identification and measurement of the concentration. The second part is on the toxicity study, try to address whether the microplastic can cause certain toxic effect to humans. And the last one, we also did some study on development of certain treatment technology to deal with the microplastic that may exist in our water source. Okay, if you look at the microplastic, it's almost everywhere. It has been a hot topic in the last few years. If you look at BBC, if you look at other several news medium, people already have some report and raise a concern that whether the drinking water that we have every day have certain microplastic inside or not. In fact, some research already shows that even in the White House, the drinking water have certain microplastic inside. However, we are also not so sure whether the reported data is really tell us the real situation or not. So that's the reason we have conduct a research project which lasts for several years, about 4 years, and looking at these 3 aspects on the microplastic. So if you look at the microplastic, it's actually due to production and the application of a lot of plastic materials. And if you look at the plastics, essentially once they are in our mother nature under the UV light, you actually will see the plastic go through certain degradation physically, chemically, and it was a very small particles, which we call a microplastic. And nowadays people also concerned about the nanoplastic, which is much smaller than the microplastic. The speculation actually in the area of whether the microplastic can absorb contaminate such as heavy metal, whether the microplastic or nanoplastic can bypass our water treatment system and eventually stay in our drinking water, and these are all the concerns. So in the first part of this research work, we have done a certain research work for a few years. So basically, we developed coloring methods, a chemical that can color the microplastic, and this actually only mainly for the plastic. As you can see over here, this is the picture under the fluorescent microscope after we put out this chemical together with the water sample. We can see the microplastic can be seen under the microscope, and we also use a FTIR to identify whether the material we saw was really microplastic or not. So we done the study, and this study shows that some of the material actually is PA, some of the material actually is PE. We also did a survey, and this is a very interesting data. So in the Southeast Asia, we took the water sample from the reservoir. We actually found out that 1 cubic meter of the water, it contained about 400 pieces of microplastic inside. So it's actually, the data is not as bad as normally what people have report. People speculate that in the water you got a lot of plastic, but our data actually shows that the plastic content actually is not that high. And we look at the water, and we did a measurement of the microplastic and the chemistry. We actually see PP, PS. These two are the major plastic material inside of the sample. We also did another study to look at the toxicity of the microplastic. So as you can see over here, we have factor A and factor B. So for example, if you look at this diagram, we get factor A, which is PVC. Factor B is one chemical, which is toxic chemical. So when we look at this data, when you have the A and B, they demonstrate certain toxicity. However, when we put A and B together, we can see the toxicity increase. All right. So in such different cases, we can see a different increase. So this means that the microplastic may already absorb certain contaminant and therefore cause enhancement in the toxicity, which is a little bit troublesome to humans. Another topic which we look at is this: whether we use an existing technology to treat the microplastic, and whether the efficiency can tell us that the microplastic is not a matter of concern just because of the process can remove the plastic material. So instead of using a very conventional water treatment process, we actually use a membrane filtration process for the removal of the microplastic. So this is some of the data. As you can see over here, you have small dot over this area, which is a membrane. Just due to the filtration, and after the filtration, the microplastic actually are captured inside of the membrane material. All right, and we try to use a different chemical for the treatment. For example, use a coagulant. You can see was the different concentration of the coagulant. The treatment in terms of the filtration pressure demonstrate different. So when you have a little bit more coagulant in the water, the filtration require lower pressure. This means that the coagulant actually is helping the filtration process, reducing the so-called fouling problem. We also look at things like a raw water. The tap water was a microplastic, and also we look at the raw water together with the microplastic. As you can see here, when you have the untreated water together with the microplastic, the pressure actually is quite high. So means that was these two substance, which is raw water and the microplastic, it can cause higher fouling problem on the surface of the membrane. And in this case, we did not add the coagulant. In this case, we actually add the coagulant. So adding the coagulant actually will helping the water filtration operation. So another issue is that can we remove the substance that cause the fouling, because microplastic actually is an important factor causing the fouling. So in this filtration operation, we run the operation continuously. However, we stop for a very short period of time, about 1 minute, and then we create a turbulence by shaking the membrane, okay, either in this direction or this direction. So after the shaking effect, we can actually see that the fouling actually become quite small, or the fouling become less severe. So was this, we can conclude that was a certain chemical coagulant, it will help to improve the filtration efficiency, and at the same time, when we create turbulence to the membrane, it can actually ease the problem of the membrane fouling. So lastly, this is just a quick summary of what we have done. We developed a method for measurement of microplastic concentration in the water. We look at the toxicity of the microplastic. We also try to optimize the treatment technology for the removal of the microplastic for production of drinking water. So with this, I thank you very much for your attention. And if you have any question, please ask me. Thank you very much.
Right then, thank you, Paul. And for the final time today then, if there are any questions, please type them into the questions box on the GoToWebinar portal. We'll just pause for a moment. Okay, nothing has come through, so I think we'll move on. So thank you, Paul.
Thank you.
And we have now reached the end of our technical presentations, which means it's time to announce the winner of the IChemE 2020 Water Award. First, though, we have our highly commended entries, and they are the joint entry from Saudi Aramco and King Fahd University and Trailblazer Technologies. So well done to everyone involved in those entries. Now it's time to announce the winner. So ladies and gentlemen, the winner of the IChemE 2020 Water Award, sponsored by the IChemE Water Special Interest Group, is AquaB. So a big congratulations to everybody at AquaB. Niall, if you're still with us, do come back onto the call and tell us how it feels to be the IChemE 2020 Water Award winner.
Hello, can you hear me? I feel delighted. Thanks so much for the very big endorsement. This is very important, and we're very, very grateful. There was a very, very high standard today from all of the presentations, which I particularly enjoyed. I was fascinated by the acoustophoresis one myself, actually, but really delighted to hear this. Thank you very much.
And is there anyone else you'd like to thank while we're still on the call?
Oh yes, I'd like to thank my colleague Mohammed Ratzagani, and also Nova UCD, the Technology Transfer Office, for their help. Thank you.
Okay, well look, thank you, Niall, and congratulations once again to everyone at AquaB, winner of the IChemE 2020 Water Award. Thank you to all of our finalists and everybody who's been with us today. I hope you've all been suitably inspired by the work you've seen presented. Don't forget, we have got other IChemE Global Award webinars coming thick and fast throughout November, so do join us for more if you can. But for now, goodbye and congratulations once again to both of today's winners.